Welcome back to Probability and Statistics 1. We are talking about color sequences with replacement. This is a random process in which we have an urn that contains a certain number of red balls and a certain number of green balls, and we're drawing a ball at a time out of the urn, noting its color, putting the ball back in the urn, and then making another random selection from the urn, and so on. And what we're interested in is the colors that come out of that sequence. What is the sequence of colors that we draw from the urn? And so we've discussed this process in the previous two videos, and we're going to continue that today. We're going to talk about the number of successes. In other words, the number of, we're calling a red ball a success, just kind of arbitrarily here. And we'd like to know if in the first n trials, so little n stands for the number of trials here, how many successes, how many red balls did we draw? That number we're denoting by capital N sub little n. So capital N sub little n refers to the number of red balls drawn in the first n trials. And we've already seen that variable can be written in terms of the indicator variables, right? The indicator variables I sub k are equal to 0 if the kth ball is green and 1 if the kth ball is red. So if I add up the indicators from 1 to n, I'll get a bunch of zeros and ones, zeros for every red ball, zeros for every green ball, ones for every red ball. So that sum will just be the number of red balls. And n sub n is known as a binomial random variable with parameters n and p. P is, of course, our success probability, which we already know is just the total ratio of red balls in the urn. And as usual, what we want to do is describe n completely. In other words, we want to know what its mean is, what its variance is. We also actually want to know the probability mass function for n. And Theorem 3.11 here gives you the expected value of n, which is n times p, the expected value of the square of n, and the expected value of the variance of n. Looking at those, the first bullet point, the expected value of n being little n times p, is actually quite sensible, right? Like if I told you that the probability of drawing a red ball is 46%, and I said, now let's draw 100 balls, how many would you expect to be red? You would say, well, 46, right, on average. And 46 is just that success probability, p equals 0.46, times the number of samples, n equal 100. And that's how you get that. So in general, that's true. The expected number of successes is just the number of trials times the probability of a success, n times p. The expected value of n squared, you see the formula there. I won't go into it much right here because it's mainly useful in computing the variance of n, which is given in that third bullet point. And that's just the sample size times the success probability times the failure probability. That turns out to be the variance of n. So let's look at the proof, and I'll go through this kind of fast. You can always go back and review the slides, but it's not really too hard, especially the expected value of n. We can use the fact that n is the sum of these indicator values, and so therefore the expected value of n is the expected value of the sum. But we know that expected value is linear, and so the expected value of the sum is the sum of the expected values. And then we also know from our previous theorem that the expected value of each I sub k is just p. So that means we have a sum of n copies of p, which is just np. And that, therefore, is our expected value. So that result follows real easily from basic properties of expected value and basic properties of the indicator variable. For the expected value of the square, it's a little more complicated because we have to do some manipulations with that formula. But again, it depends on the fact that n is the sum of those indicator values. So the expected value of n squared would be the expected value of the square of the sum. Now, if you expand that sum, you get the expression there in the second line. The sum of the I sub k squared is equal to the sum of the squares of the I sub k's plus the sum over all pairs kj, where k does not equal j, of I sub k times I sub j. And if you like, you should try that with a like a sum of like I1 plus I2 plus I3. Go ahead and square that out, and you'll see exactly what we mean there and why that general formula is true. Now, once you have that middle line, you can apply the properties of expected value, namely that it's linear, right? So the expected value of a sum is the sum of the expected values. And that gets us to the third line. We'll have the sum from k equal 1 to n of the expected value of I sub k squared plus the sum over all pairs k comma j, such that k is not equal to j, of the expected value of I sub k times I sub j. Now, the first sum we can handle pretty easily because we know from our previous theorem that the expected value of I sub k squared is also p. So that sum is just the sum of n copies of p, and it's again n times p. So that's that first term there. Now we want to consider the second term in equation 2 here, the sum over all pairs of the expected value of ik times ij. So first of all, let's consider that random variable, ik times ij, where k is not equal to j. The possible values are 0 and 1, right? Because each ik and ij is either 0 or 1, and a product of either zeros or ones is either going to be 0 or 1. So to think about what that product is, just think about the event that ik times ij equals 1. The only way that could happen is if ik is 1 and ij is 1 simultaneously, right? And we can compute that probability pretty quickly because, just think about a color sequence of length k in which the last entry is red and also one entry before is known to be red. So how many ways can that occur? Well, we'd have R choices for the kth red ball. We'd also have R choices for the jth entry, which is supposed to be red. And then for all the other k minus 2 entries, they can be any color whatsoever. And so we'd have R plus G choices for each of those. And then we would have, of course, in the bottom, the total sample space size would be R plus G to the k, because you have R plus G choices for the first ball, R plus G choices for the second ball, and so on, all the way out to ball number k. And then if you just cancel that out, you find that that's just p squared. So that means that ik times ij is 1 with probability p squared. The only other value you could possibly have is 0, and so that has to happen with probability 1 minus p squared. And there we have the probability distribution function for ik times ij. And therefore the expected value of ik times ij would be 1 times p squared plus 0 times 1 minus p squared, or just p squared. And now we see that that second sum in the previous slide, the sum of expected values of ik times ij, is just the sum of a whole bunch of p squareds. The question is, how many? Well, look, we're summing over all pairs kj such that k does not equal to j. And remember, k and j are just indices between 1 and n. So how many indices are there that are like that? Well, you have n choices for k, right? And then how many choices do you have for j? You would have n minus 1, because j can't equal k. So there's n times n minus 1 terms in the sum. Each of those terms is equal to p squared, so the sum has to be n times n minus 1 times p squared. Now if we put all that together, we find that, going back to this slide, if you look at equation 2 there, we found that the first sum was n times p, and the second sum was n times n minus 1 times p squared. And that's what we're seeing right here. So the expected value of n squared is np plus n times n minus 1 times p squared. And now we'll use our alternate form for variance, of the formula for variance, to find the variance. The variance of n would be the expected value of n squared minus the expected value of n, the quantity squared. And we know both of those now. the expected value of n squared is np plus n times n minus 1 times p squared minus n, and then the expected value of n quantity squared will just be n squared p squared. And you manipulate that algebraically and you get the result that the variance of n is little np times 1 minus p. So that gives us the theorem 3.11. It gives us the expected value of n, which is np, and the variance of n, which is n times p times 1 minus p. The complete picture for the distribution of the number of successes, this capital N, would be given by the probability mass function, right? That's the function whose value at an integer m is simply the probability that n sub n equals m. So how would we compute that? Well, you want to think about it this way. Think about the event that n sub little n equals m. That is the event that there's exactly m red balls in the first n balls that are drawn. What color sequences would we be talking about here? We'd be talking about color sequences that have length n, because there were n balls drawn in all, and exactly m of those entries would be 1s, and the rest would be 0s, right? Because we want exactly m red balls. Now, all those color sequences are disjoint, right? And they have exactly m1s in them, and exactly n minus m zeros in them. So the probability of any one of those color sequences would be, according to theorem 3.8, p, our success probability raised to the number of 1s, so that would be p raised to the m, times our failure probability raised to the number of zeros, and so that'd be 1 minus p to the n minus m. Now, so that's the probability of each one of those color sequences. The event n sub n equals m is the union of all those color sequences, right? The union of all color sequences of length n which contain exactly m1s. How many of those are there? Well, there's n choose m, because you can think of this as just a process of taking a strength of length n, choosing m of those entries to put the 1s in, so there's n choose m ways of doing that, and then putting zeros in the remaining entries. There's just one way of doing that. So the number of those color sequences is n choose m, and that gets us to theorem 3.12. The probability mass function for the number of successes, the number of red balls in the first n trials, is the probability that that number of successes equals m is equal to n choose m times p to the m times 1 minus p raised to the n minus m. And that function is known as the binomial distribution with parameters n and p. Here I've got a few graphs that just show that distribution function, that mass function, for various values of n and p. Here we're looking at the binomial distribution for n equal 8 and p equal 1/3. So we're 8 trials, and the success probability is 1/3 on each trial. And we're looking for the probability of drawing exactly m red balls in these first 8 trials. So when you can see from the graph that when m is 0, the probability of drawing exactly 0 red balls in 8 trials looks like it's about 0.04. The probability that you would draw exactly one red ball looks about like it's 0.16, and so on, about those numbers. Here's the distribution when n equals 12 and p equals 1/2. And so you see now the distribution is shifted a little bit to the right. It's more sort of symmetric because p is 1/2. And you can see that, for instance, the most likely value of the number of successes would be n equals 5, right? And the probability of that would be a little bit over 0.22. Here's the probability when you have drawing 20 balls and the success probability is 2/3. You can see it shifted out more to the right, so that is the binomial distribution with n equal 20, p equal 2/3. We'll end this with a few discussion questions. Suppose I pick a card at random from a standard deck, record its suit and its value, so like, Queen of Hearts. Then replace it in the deck and repeat 4 more times. What's the probability that exactly one of the first 5 cards is a face card? Well, this doesn't sound like a color sequence problem, but you can really think of it that way. If you're interested in face cards, just think of those as your successes. Those are the red balls. Everything else is a green ball. So since there are how many face cards? 3 times 4, there's 12 face cards in a deck. So there's 12 red balls, and that would mean there's 40 green balls. And now you're looking for the probability of exactly 1 success in 5 trials. So that would be the probability that n sub 5 equals 1 when you have a success probability of 12 out of 52, right? So you could use the color sequence process to answer this question. And I suggest you think about that in similar fashion when you look at the remaining 3 questions here. See if you can translate it into some sort of equivalent color sequence probability, and then use what we've done to compute that probability. We'll pick up again next time, and we'll look at another random variable associated with the color sequence process, namely the trial number of like the 5th success. On what trial number does the 5th red ball or the 6th red ball or so on? When do those appear? Those are called the negative binomial random variables, and we'll discuss those in our next little installment. In the meantime, y'all take care. Let me know if you have questions, and we'll talk to you again real soon.